Hello. Today we're going to be looking at the star-delta transform for electrical circuits. It's also known as the T-delta transform, the Wye-Delta transform, or the Wye-Delta transform spelt W-Y-E. They're all the same thing. In order to understand the star-delta transform, we need first to understand the concept of electrical equivalence. Suppose we've got two networks, 1 and 2, each of which are some configuration of resistors, but we don't know what these configurations are. There are three connections into these networks, A, B and C. For both networks, we apply voltages VA, VB and VC, and we measure the currents. For network 1, they're IA, IB, IC, and for network 2, they're IA bar, IB bar and IC bar. Then networks 1 and 2 are said to be electrically equivalent if IA is equal to IA bar, and similarly for B and C, for any voltages VA, VB, VC. The significance of electrical equivalence is that you can swap the arrangement of resistors that were in network 1 for the arrangement of resistors that were in network 2, and the rest of the circuit will be completely unaffected. There are two uses for this process. One is that it can allow you to turn complex circuits into simpler circuits. And secondly, it enables circuits to be analysed more straightforwardly by hand. So the star-delta transform is all about where we have two networks, A and B, and in one case we have three resistors arranged in a star, and in the second case, B, they're arranged in a triangle, a delta shape. And what we do is to calculate the resistor values in one network as a function of the resistor values in the other, such that the networks are equivalent. So let's think first of all about the currents flowing through network A. We don't know the potential at the centre of the star, so we're going to call that V. And therefore IA is given by voltage over resistance, in other words VA minus V over RA. And similarly IB is VB minus V over RB, and so on for IC. Now that's fine, but the problem is that we don't know what V is. But what we do have is Kirchoff's first law, and that tells us that the sum of the currents going into the centre of the star sum to 0. In other words, IA plus IB plus IC is equal to 0. So therefore 0 is VA minus V over RA plus VB minus V over RB plus VC minus V over RC. What we now do is to gather terms involving V and take them over to the left-hand side. Take the V out. That gives us V into 1 over RA plus 1 over RB plus 1 over RC is equal to VA over RA plus VB over RB plus VC over RC. We then divide by the factor that's multiplying V, and that gives us an expression for V. We now substitute this value of V into the expression for IA, and from here it's a matter of putting everything under a common denominator, multiplying top and bottom by RC, and a little bit of tidying up, to give an expression for IA, which is of the form VA minus VB multiplied by some function of the resistor values, plus VA minus VC multiplied by some function of the resistor values. Now let's analyse network B. There it's a much more straightforward calculation. IA is equal to the current flow between A and B plus the current flow from A to C. So consequently IA is VA minus VC over RCA plus VA minus VB over RAB. Now if networks A and B are to be equivalent, then it must be the case that the numbers which multiply the expressions VA minus VC and VA minus VB are the same for both networks. So for example, we require that 1 over RCA is equal to RB over RA RB plus RB RC plus RC RA. Taking the reciprocal of both sides and applying that to all the other nodes gives you the expressions for RCA, RAB and RBC in terms of RA, RB, RC, such that the delta network is equivalent to the star network. But what about if we'd have wanted to do the calculation the other way round? In other words, if we start from the delta network and want to calculate the resistor values in the star configuration, what we need to do is to take equations 1, 2 and 3 and rearrange so that RA, RB and RC become the subjects of the equation. The easiest way to do that is to let mu be equal to the numerator of the right-hand side of each of equations 1, 2 and 3. In other words, mu is RA, RB plus RB, RC plus RC, RA. Equations 1, 2 and 3 can then be rearranged to give RB equals mu over RCA, RC is mu over RAB, and RA is mu over RBC. That's fine, but the problem is we don't know what mu is. But what we can do is to substitute these expressions for RA, RB, RC into equation 4. If we do that, on the left-hand side, we just have mu. On the right-hand side, we have terms each of which involve mu squared. So we can divide both sides by mu, which we know isn't 0, take mu out as a factor, rearrange, and that gives mu as being RAB, RBC, RCA over RCA plus RAB plus RBC. Now we can substitute this value of mu into the expressions we had above for RA, RB, RC. And if we do that, what we end up with are the conversions to go from a delta to a star network. So there we have it, the formulae for converting from a star network to a delta network, and from a delta network to a star network. The one other point to make is that all of the above formulae work equally well if you have capacitors and inductors in the circuits as well. And therefore, if you're comfortable working with impedances instead of resistors, you can replace R by Z in all of the above diagrams and calculations, and everything will work just fine.